Good afternoon, everyone. So this is my next lecture based on photodiodes. In the last lecture, we have discussed about lasers and LED, which are also semiconductor devices. There is another category of devices which is called as photodiodes. So these, in the case of the lasers and LEDs, we have seen that we have population inversion in the case of the laser. While in the case of the LEDs, we don't have any kind of population inversion. Also, we have seen that laser is basically a coherent emission source, while LED is non-coherent source. So, wherever there is a requirement of laser, we use in industry lasers along with optical fibers, and wherever we require LEDs, we use along with fibers or different components in the industry LEDs. So, in the same way we discuss about now we are going to discuss this photodiodes, and in these photodiodes we have to see in the same way like in lasers and LED we have constructed laser and LED with the help of the PN junction. So, in the photodiodes we also construct that with the help of the PN junction, but in the reverse biasing case. Normally in lasers and LED we used forward biasing conditions, here we use reverse biasing condition. So, coming to the photodetectors, the detectors basically detect the optical signal coming to an optical fiber system, and it is one of the crucial element. It is basically used to convert the received optical signal into an electrical one. Then after it is converted into an electrical signal, then it is amplified with the help of different processing units. So, what we are having here, that photodetectors are a particular type of component which is used for converting an optical signal into an electrical one, and then it is further processing with the help of different type of electrical amplifiers. So, there are some performance and compatibility requirements for the detectors, so that it can be easily coupled with the fibers at the output. So, it should have a small size, it is made up of a suitable material. So, normally we use third and fifth group elements for making LEDs and lasers. In the same way we use third and fifth group elements for like what we have, aluminum gallium arsenide or indium gallium phosphide for the case of the detectors. So, we must have the small size of the detector, it must have a suitable material, third or fifth group element from the periodic table, high sensitivity at the operating wavelength, it should have a at a very high wavelength or at a nominal wavelength, it can be very high, must have a high sensitivity, whether we are operating the detector at a wavelength of 800 nanometer or we are detecting the light with the detector of wavelength 1300 to 1500 to 1600 nanometers. So, in these high range of wavelength it can be high sensitive, and also for the lower wavelengths like 800 to 900 nanometer. It has fast speed, short response time to obtain a suitable bandwidth. It has sufficient bandwidth to handle very high data rate. So, normally we use nowadays in the optical fiber we are using gigahertz range or gigabits, the data we are sending with the fiber. So, sufficient bandwidth to handle very high data rate, it must have low cost with high reliability, a minimum noise introduced by the detector. Normally in the lasers and LED we have different type of noises like short noise, quantum noise, thermal noise and other noises like dark noise. In the same way the detector also have different type of noises like dark currents, leakage currents and shunt conductance, and these noises must be low in order to receive a proper signal at the receiver or at the detector. So, the physical principle of photodiode is based on obviously on the PN junction diode or a PN diode. This device is reverse biased. So, this is an important point. In the case of the lasers and LEDs, these will work in forward biased, but the device which is basically a detector is working in a reverse bias, and the electric field developed across the PN junction sweeps mobile carriers holes and electrons to their respective majority sites. So when you are providing a reverse biasing, as in the case of the p-n junction, what will happen? The holes, majority holes in the p-type semiconductor will get attracted towards the n-type of polarity we are providing as a biasing, and similarly the electrons in the n side will be attracted towards the p type of polarity we are providing through the biasing. So that's why they will move towards the terminals or the ends of the p-n junction, not across the junctions. So obviously there will be a broader depletion region as compared to the case when we are using in the case of the forward biasing or in the case of the lasers or LED. So a depletion region, or it is called as active region or layer, is therefore created on the either side of the junction. However, the field accelerate minority carriers from both the sides to the opposite sides of the p-n junction, forming the reverse leakage current of the diode. So there will be a less current flowing through this type of photodiode, and this is called as leakage current or the reverse leakage current across the diode. So a photon incident in or near the depletion region of this device, which has an energy greater than h nu is greater than must be Eg, will excite an electron from the valence band into the conduction band, and this process leaves an empty hole in the valence band, and it is known as the photogeneration of electron hole pair. So in the same way we have discussed already in the case of the lasers and LED, there the recombination of electron hole pair will provide you lights. In the same way, whenever the light falls on the detector, it will provide you electron hole pair in the active layer. So carrier pairs so generated near the junctions are separated or sweep or drift under the influence of the electric field. So whatever the carrier pairs are generated in the active region, they will get influenced by the electric field and they will separate it under the electric field, and there will be a drifting of the carriers across the junction. The drifting is very slow or very low, and that is why the leakage current is also very low in the case of the reverse bias detectors. So we can see from the figure here that we have p-n junction, but here we are providing reverse biasing. P type of semiconductor is connected to negative terminal and n type of semiconductor is connected to positive terminal. So that is why what will happen, the number of electrons in the whatever the number of electrons or the minority carriers in the p side, obviously it is electron in the p side, this will move towards the n side. Similarly, the holes in the n side, which is minority carrier in the n side, will move towards the p side, and there will be a formation of the depletion region which is much wider as compared to the case of the lasers and LED. So here the first requirement is h nu must be greater than Eg, the energy which we are providing for transition of electrons and hole towards different terminals. It must be greater than Eg. Only in that case the depletion region gets wider, and there will be formation of, there will be some leakage current will flow in the p-n junction. So basically photodiode will give you an idea about how optical signal will be converted into electrical one, and then it will be further transmitted to an electrical amplifiers, and there we can easily amplify the signals. So there are different types of photodetectors or photodiodes. We have basically two kinds of photodetectors. The first one is a pin photodetector. So in the pin type of structure, we have a p layer, a I layer, which is called as intrinsic layer. So this layer is called as intrinsic layer. So the device structure consists of p and n type of region separated by very lightly doped in n I intrinsic region. In normal operation, a sufficiently large reverse bias voltage is applied across the device so that intrinsic region is fully depleted of the carriers. So here when we provide a negative biasing, that is negative terminal is connected with the p side and positive to the n side, obviously the electron hole pair get repelled from each other, or they get generated from the light, and they will transmit towards their opposite poles. So holes will come towards, because it is a negative polarity, holes will attract towards the negative polarity and electrons will attract towards the positive polarity. So there will be less flow of current due to these minority charge carriers. So in the next figure we have shown the representation of the PIN photodiode circuit with an applied reverse bias. As we apply the reverse bias, there will be a change in the optical power. So, obviously the optical power is high initially, but it decays slowly as when we provide the biasing. So, initially the power is P naught, and after a particular width or a depletion width W, the power drops down. So, these figures will show how the working of the photodiode actually is and how the power will drop down in the case of the photodiodes. So, we have the high electric current will flow in the photodiode when we convert that optical signal into electrical signal. So, next we have some points regarding how these photodiodes will work. So, when an incident photon has an energy greater than or equivalent to band gap energy, obviously we have to see that whatever the photon is incident on the electron on the or the atom at the lower energy level, it must be greater than the band gap energy of the semiconducting material. Only in that case the electrons will transmit or excite from valence band to the conduction band. So, this process generate mobile electron hole pair. So, these electron hole pair are known as photocarriers, and since they are photon generated carriers, they are available to produce current flow. So, when a bias is applied across the device, the photodetectors are designed so such that carriers are generated in the depletion region where most of the incident light is absorbed. So, mostly the light is falling on the active layer and or the depletion region, and in that region only the carriers are generated. So, electron hole pair generated in the active region. So, first point which is important, that active layer and electron hole pairs is generation. So, in the active layer the electron hole pair is generated, and a high electric field present in the depletion region causes these carriers to drift across the junction, and that is why there will be a rise of the current flow in an external circuitry, and this current is particularly known as a photo current. So, this is something about how the photo current generated in the photodetectors in a PIN type of photodetector. So, at a particular lower wavelength end, the photo response cuts off as a result of very large values AS. So, we have in the depletion region has a width from equation, that is P absorbed is equivalent to integration over 0 to W, that is where W is the width of the depletion region, alpha S is the absorption coefficient, P in is the input power exponential minus alpha S into X dx and multiplied by P in 1 minus e to the power minus alpha S W. This particular term shows the power drop. So, whatever the incident power, it is dropped by the factor P in e to the power minus alpha S W. So, if we take into account the reflectivity RF at the entrance phase of the photodiode, then the primary photocurrent, whatever the photocurrent is generated with the help of this P absorbed is given by IP, which is equivalent to Q upon H nu P in 1 minus e to the power minus alpha S W 1 minus RF, where RF is the reflectivity of the at the entrance. So, RF is here reflectivity. So, these equations are important. The first equation will give you an idea about how much power is absorbed in the depletion region. So, whatever the incident power, and there is some leakage current and there is some absorbed power. Due to this absorbed power, how much is the photocurrent generated in the photodetector? So, this is given by this formula, that is Q upon H nu P in 1 minus e to the power minus alpha S W 1 minus RF. So, if we know the value of the RF, the reflectance, if we know the value of the absorption coefficient, that is alpha S, W is the depletion width, P in is the incident power, Q is the charge of the carriers, H nu is a constant value where H is the Planck's constant and nu will be given to you, that is in the numerical problems, that is the wavelength in terms of wavelength or in terms of frequency. By this formula we can easily calculate the value of the photocurrent. So, next there is an important parameter in detectors which is called as quantum efficiency. So, obviously when the word comes efficiency, we have to see how many electron hole pairs generated at the photodetector divided by number of incident photons. So, we have to see how much is the incident photon and how much is the electron hole pair generated due to these incident photon. This will give you an idea about what is the quantum efficiency or the efficiency of the photodetector. So it is normally defined with the term eta, and quantum efficiency is the fraction of the incident photons which are absorbed by the photodetector and generate electrons which are collected at the detector terminal. So here eta is given by number of electron hole pairs generated divided by number of incident photons. So what will be the electron hole pair generated is your photocurrent divided by Q, which is the charge, and number of incident photon is given by power P in divided by h nu. So with this formula we can calculate the value of eta. So if we know the value of IP, Pn and wavelength, we can easily find out the value of the quantum efficiency or eta. Here IP is the photocurrent generated by steady state optical power P in incident on the photodetector, and eta is also given by Re upon Rp, where Rp is the incident photon rate, photon per second, and Re is the corresponding electron rate. So this is a new formula for eta. There are two formulas for eta. So we can calculate by any of the formula if we know the parameters. So if we know the value of the Re and Rp, we can easily calculate the value of the eta, that is quantum efficiency. So the quantum efficiency is generally less than unity. Not at all of the, obviously not at all of the incident photon is converted into an electrical signal or electron hole pair generation. So obviously eta must be less than 1, or equivalent to 1. So normally it is less than unity. So next we have responsivity, which is defined by a term R. So the expression for quantum efficiency does not involve photon energy. So therefore there is a new term which is called as responsivity, and it is defined by R and is often of more use when characterizing the performance of a photodetector. So we have R, which is given by IP upon P naught. So it is IP is your photocurrent. So IP here is photocurrent and P naught is the output power from the channel or from the fiber. So R is equivalent to IP upon P naught. Its unit is in ampere per watt. So where IP is the output photocurrent in ampere and P naught is the incident optical power. So in watts, so incident optical power, or you can say output power from the fiber. So incident optical power is basically the same thing as the output optical power from the fiber. So the responsivity is useful parameter, and it gives the transfer characteristic of the detector, that is basically photocurrent per unit incident optical power. So we have R is equivalent to IP upon P naught, or we can calculate with this formula also. R is equivalent to eta Q upon h nu. So by this way, if we know the value of the IP photocurrent and the incident power at the detector, we can calculate the value of the R, or with the help of eta, that is the efficiency. If we know the efficiency of the photodetector and the wavelength at which the photodetector is working, we can also calculate the value of the responsivity. So next category of photodetectors are avalanche photodiode. So as we know the term avalanche, and we have already discussed about avalanche gain. So the pin photodiode doesn't have a particular type of gain as compared to the avalanche photodiode. So avalanche photodiode is having the same structure as the pin structure, but it has a gain mechanism in this. So we provide the reverse biasing in the case of the avalanche photodiode, but here with the help of the one photon we create more number of electron hole one electron hole pair, and then that electron hole pair hits another electron hole pair, and they will create another electron hole pair. So that's why there will be a chain type of mechanism occur in the case of the avalanche photodiode. So avalanche photodiode uses the avalanche process to provide additional performance. So this additional performance is basically your gain. So if we want to calculate the signal to noise ratio in the case of the avalanche photodiode, then we can easily see that the gain factor here will make the signal more useful at the detector as compared to the pin photodiode. So whenever we require in the industrial application, like we have to increase the gain of the output, then we can use avalanche type of photodiode or photodetectors. So the avalanche photodiode possesses a similar structure to that of the pin or the PN photodiode, and avalanche photodiode structure similar to that of a Schottky photodiode. We have already discussed about Schottky photodiode. The main difference of the avalanche photodiode to other forms of photodiode is that it operates under the high reverse bias condition. So, there is basic requirement, that is it must have a high reverse bias condition. So, this enables avalanche multiplication process, and there is a multiplication factor given by M, which is equivalent to I upon IP. So, in numerical problems we see that we can put when we calculate the value of signal to noise ratio. So, in that case I will be converted, or I will be replaced by M into IP. So, this enables avalanche multiplication of the holes and electrons created by the photon light impact. So, here there is a term called as impact ionization. So, impact ionization is basically hitting of one electron hole pair and then creating one electron hole pair, and then these electron hole pair will hit another electron hole pair and they will create more number of electron hole pairs. So, this process is called impact ionization. So, carrier hitting is basically the concept behind the impact ionization. So, as a photon enters the depletion region and creates an electron hole pair, these charge carriers will be pulled by the very high electric field away from one another. So, in this field region, photo-generated electrons and holes can gain enough energy so that they ionizes bound electrons. So, whatever the bound electron hole pair, they ionizes that and they will again create one electron hole pair. So, with the help of one electron hole pair, there will be much more number of electron hole pair. So, their velocity will increase to such an extent that when they collide with the lattice, they will create further electron hole pairs, what I am saying about. So, whatever I have said, that they are in the process of creating more number of electron hole pair as compared to the pin photodiode. So, this carrier multiplication is known as impact ionization, and this newly created carriers are further accelerated by the high electric field, thus gaining enough energy to cause further impact ionization. So, this phenomena is known as avalanche effect, and obviously this will provide you better gain as compared to the pin photodiode. So, the avalanche action enables the gain of the diode to be increased many times, providing a very much greater level of sensitivity. So, for a smaller wavelength it is much sensitive, and for a higher wavelength it is also much sensitive, as in the case of the pin photodiode maybe they will not be sensitive for much higher wavelengths. But the avalanche, because of the impact ionization process, and in avalanche photodiode these are much sensitive to higher wavelengths also. So, we have a diagram here for reach through avalanche photodiode structure and electric field in the depletion and multiplication region. So, here we have a structure like in the case of the pin photodiode we have only P, I and N type of a structure. Here we have N plus P, I, P plus type of structure. So, I is the intrinsic region. Obviously, the avalanche region is in between the N plus to P region, because it is a kind of a PN junction. Then there will be a region which is required for impact ionization. So, this particular region, the stable region, is basically impact ionization region, and there is a minimum requirement for impact ionization region which is shown here. At this point a maximum field required for impact ionization. So, common structure for achieving this carrier multiplication is reach through avalanche photodiode. It is called as reach through avalanche photodiode, and in short it is called as RAPD. So, when a low reverse bias voltage is applied, most of the potential across the PN junction will get dropped, and this depletion layer widens with increasing reverse bias voltage. So, when you increase the reverse bias voltage to maximum content, there will be increase in the depletion region, and the impact ionization is much more in the case of this particular thing. So, it's required in the case of the avalanche photodiode, it must have a large reverse bias voltage, as not in the case of the pin photodiode. So, the multiplication factor for the avalanche photodiode is given by M, and it is given by I upon IP or IM upon IP, and where IM is the average multiplied output current and IP is the primary unmultiplied photocurrent. So, analogous to the pin photodiode, the performance of the APD is characterized by its responsivity, and here R is responsivity of the avalanche photodiode is given by a factor. Multiplication factor is included here because obviously M is equivalent to IM upon IP. So, here we have NQ IM upon IP divided by H nu, or we can write it as R into M. So, here RAPD is equivalent to R into M. So, this is for pin photodiode, and this is the multiplication factor, and this is for avalanche photodiode. So, obviously the responsivity is also much higher as compared to the pin photodiode. So, we have much more responsivity of avalanche photodiode as compared to the pin photodiode. So, in this lecture we have discussed about different type of photodetectors, how these detectors will work in the case of the reverse biasing. Either it can be a pin type or avalanche photodiode. We can see different applications of these diodes in industries, or we can use as in the case of the optical fiber, we can use these detectors, because if we want to build a project on based on lasers and detectors, we have to see what type of channel we require at both the ends. So, optical fiber or the optical medium is much better choice for these. That is why we nowadays we are using lasers with optical fibers, and there is pin or avalanche photodiode you can use. So, thank you so much. This is all about the photodetectors, and you can apply these photodetectors and concepts and lasers and LED concepts in different type of other projects also. So, as I have said that in the case of the optical fiber design or a bench design, you can use it. Thank you so much.